right, so we're going to be looking at Newton's second law here. We're going to first look at the lab we did previously, looking at Newton's second law before we jump into the math. All right, so first off, in part one of Newton's second law lab, we were studying the relationship between the force applied to a cart and measured its acceleration. And we got something like this, right, where we can see that, all right, since it's a nice straight line like that, it tells us that force is directly proportional to the acceleration. Okay? Pretty straightforward, and this makes sense. If you push on something, all right, that force can cause it to accelerate. If you push twice as hard, it's going to accelerate twice as much. All right. Second part was a little bit more involved. We were keeping the mass the same this time. All right. Or excuse me, we're keeping the force the same in the second part. And then we were studying how, as we decrease the mass, what happens to the acceleration. And we get a graph like this. And this could indicate that they are inversely proportional. One is definitely increasing while the other is decreasing. But the question is, are they doing that at the same rate? So one way that I had you guys do that was to take the mass and take its inverse. Because if you take that inverse, graph it, and if they are form a straight line, then you know that they are inversely proportional. And lo and behold, when you did, you sure got a nice proportional line like this, which means that the acceleration is inversely proportional to the mass. So let's take a look at Newton's second law. All right. Newton's second law states that the acceleration produced by a net force on an object is directly proportional to the net force and is in the same direction as that net force. So that's basically part one. All right. The cart accelerated in the same direction as the net force. All right. That string, aka pulling on the cart over the pulley. And as we increase the force, the acceleration increased proportionally. All right. And then the second half of this still relates to acceleration, but now it's looking at how acceleration and mass are related. And is inversely proportional to the mass. So as the mass decreased, acceleration went up, or vice versa. That's Newton's second law right there. And it's a little wordy, but most students have a really good understanding already how force and acceleration, or mass and acceleration, relate to each other. And these are the three equations, all right? Really, it's just one, just rearranged to solve for either the net force, the mass, or the acceleration. So let's apply this then to what we were working on last unit with force diagrams. So let's apply Newton's second law to some force diagrams here. We've got a man who pushes a child in a grocery cart. And the total mass of that child in the cart is 30 kilograms. So write that down. We're going to ignore friction. I want a force diagram, and I got to determine how hard that man is pushing to cause an acceleration of 1.5 meters per second squared. So force diagram here on Earth. So we got to have some gravity, all right, some weight. We also know that there's got to be normal force holding it up, all right, from the ground, and the man is pushing it, we'll just say to the right. Call that a push. Since you guys should remember that last unit I showed you guys that force of gravity is just the mass times the field strength. And the field strength here on Earth is 10 newtons per kilogram. So if we have 30 kilograms, that just means it's 300 newtons. So we know that and this one up here, because we already knew that they had to be equal. They were just in different directions. The push, on the other hand, we don't know. Now, we know these two guys cancel out. So the only thing left is this push. It's the unbalanced force that's going to cause this acceleration. And we know that from Newton's second law that the net force is equal to mass times acceleration. Well, the net force, whatever's left over on this force diagram after things have canceled out, is just this push. So this, for this case, it's going to just be Fp. All right. So let's solve for that. We've got the net force is equal to 30 kilograms times 1.5 meters per second squared. Now that gets me a net force of 45, but if I look at the units, I get kilograms times meter per second squared. All right. All forces are measured in newtons. So what's going on here? Well, a newton, all right, if we look at units, a newton is the amount of force or push required to take 1 kilogram object and accelerate it at 1 meters per second squared. So unit-wise, a newton is really the same thing as kilogram meter per second squared. We just wrap them up in a nice bundle. Sometimes they can be broken down. All right. So just know that a newton is really all of those units together for later on. So in other words, my net force is 45 newtons. And since that is the same thing as the push here, 45 newtons. Let's try another one. A 2 kilogram cart on a frictionless track is pulled by a force of 3 newtons. So let's draw a force diagram. We've got a cart, so force of gravity, and again, I can take my mass and multiply it by 10 to get that value of 20 newtons. All right, track is going to apply a normal force. There's also 20 newtons. We do have a pull off to the side here that causes that acceleration, and we know that it is 3 newtons. Calculate the acceleration of the cart. Well, if we look back at our equations, we know that the acceleration is equal to the net force over the mass. All right, and plug them in. Let's see what we got here. We've got a net force of, since the force of gravity and the normal force cancel itself out, we're left with just the push, or the pull here, excuse me, of 3 newtons. All right. So we know net force is equal to 3 newtons, and we know a mass is 2 kilograms. So that's our equation. Plug them in. We have acceleration is 3 newtons over 2 kilograms. So acceleration is, remember that 1.5, and newton is really the same thing as kilogram meter per second squared. All right, so, and then we are dividing that by kilograms. So those go away, and you are left with just the meters per second squared. All right. And let's do one more. 4 newton force accelerates a cart on a frictionless track at a rate of 12 meters per second squared. Draw a force diagram and determine the mass of the cart. Okay. So, again, not doing anything too complicated with these force diagrams. Let's see here. One thing that you don't want to get confused, again, this N here, that is the normal force, not the net force. Okay. We know a couple things. We know that the force accelerating it, all right, got a 4 Newton force here. What we don't know, these guys. We do know, though, again, the net force. Net force is 4 newtons. We've got an acceleration of 12 meters per second squared. We can solve for the mass. By doing this. 4 newtons over, and let me make that a little bit better so you don't think that's a 9. 12 meters per second squared. All right, so we get a mass of, we'll just say 0.33 kilograms. And if you want to see those units cancel out, again, Newton is a kilogram meter per second squared divided by meters per second squared. Those go away, leaving only kilograms. And since, all right, we got that, we can come back over here and 3.3 newtons, 3.3 newtons. And there you go. All right, that's how we do the basic force diagrams and applying Newton's second law to those.